Welcome to Lecture 24, Special Relativity. As we approach, finally, the end of this series of lectures on introductory astronomy. We're not there yet, but we're finally getting to some of the most exciting aspects of nature, of astronomy and astrophysics. And when I say most exciting, I mean the things that show up in sci-fi, movies, books, and so on. Some of the most exotic aspects and objects in the universe. But to describe those, it turns out that we need to spend a little bit of time and rewind, if you will, to kind of where we were at the first third of the semester and give some additional background. And today we're going to start doing that by discussing special relativity. So just to recap where we came from and kind of why we're talking about special relativity at all, we've spent the vast majority of the last 2 months talking about the evolution of stars. And at a high level, there are 2 different branches of that evolution that can occur. And as we've discussed it at some length, basically what determines what evolutionary path a star will take is its mass. You know, the mass of a star has again and again been the defining property that kind of determines everything else about the lifetime of a star and its evolution, and that certainly is the case here. And so low mass stars, less than 8 stellar masses, evolve along a particular branch, which is shown at the top here. And so, you know, these stars are relatively small for stars, again. When they reach the end of their main sequence lifetime, the core collapses before being sustained by the electron degeneracy pressure, and as that process occurs, the outer surface balloons out and the star transitions into a red giant. Eventually, and obviously we're skipping some steps because we're all experts in that now and I don't need to rehash it for you, though if you want it rehashed, just rewind a few videos and you can review at your heart's content. But as it approaches the end of its lifetime, if you will, it loses roughly half of its mass into the interstellar medium in the form of a planetary nebula. And the remnant, the dense, degenerate, largely carbon and oxygen core that's left, is known as a white dwarf. White because it's really hot, but not hot enough to actually fuse anything that's left. So it's really hot, but there's no energy source there. And so over time, it'll radiate as a black body, sending off that radiation into space, and it will thereby cool down. And eventually, someone coming along would be confused as to why it would be called a white dwarf anymore, because it'll be invisible, at least, well, yeah, to the human eye anyway. But it will cool down and eventually, you know, disappear from view. So those are low mass stars. The high mass stars, again, do something a little bit different. They start off larger because they have more mass. They're bluer and they burn hotter. When they reach the end of their main sequence lifetime, they turn into a red supergiant, which is the fundamental aspects of that are very similar to the red giant transition in a low mass star. We just call them supergiants because they're even bigger than the red giants. But the big difference for these high mass stars is that they die in a much more cataclysmic fashion, and in particular they explode in the form of a supernova. And you can go back and look at earlier lectures to go through the details again. But they rather than sort of the gentle planetary nebula expanding into the interstellar medium, this is a collapse, a bounce, and just obliterates the majority of the star. What's left though is a little more exotic, or a lot more exotic than the white dwarf. And there are a couple of options. One of the options that we've talked about in a little bit of detail, though not too much, is known as a neutron star, so called because it's got a lot of neutrons in it. At a gross level, you can kind of think of it as it collapses, it becomes so dense that the protons and the electrons that are there get pushed together and converted into neutrons. And so it turns out there's a lot of modern research going into the structure of neutron stars. And in particular, there's a lot of interesting work being done related to what's going on in the cores of neutron stars. What kind of matter is there? And so if you're interested in that, don't hesitate to reach out. I've actually done some work on that, but I will try not to turn this into a 5-hour lecture, just to talk about things I think are interesting. But the other possibility, if the star is massive enough, these are all massive stars we're talking about now, 8 solar masses or higher when they begin their life. But there's obviously a lot less than that left over in the stellar remnant, right? Because you go supernova, most of the mass gets blown to smithereens. There is a core remnant, typically, and that can either be a neutron star, or if it's massive enough, it can turn into a black hole. Now, black holes are just about as exciting as you get when it comes to astronomical objects. These are certainly, all over the place in sci-fi. No doubt all of you have heard of them. But you may or may not have done a whole lot of detailed study on what these things really are. So that's going to be one of the topics over the next, what remains of this set of lectures, a couple of weeks. But this is kind of where we've been and now where we're going. So, but before we get there, as I said, we actually need to back up and do a little bit of additional groundwork to sort of lay the foundation, because in order to understand the properties of these very exotic astronomical objects, it turns out that we need to talk about a little bit of physics. And I know everyone is very excited, no groaning at all. So what we're going to do then is begin by talking about something that's going to seem completely unrelated to anything that I just told you we're going to talk about, but I promise we will bring these things together. And so we're going to start off by talking about the concept of measuring speed in different reference frames. So what do we mean by that? Well, a reference frame is just a fancy scientific way of saying somebody's position, basically, and movement. And so in other words, I've got my reference frame. If I measure a position or a velocity of something, I'm going to get a particular value. But you may have a different reference frame. In fact, you almost certainly do. And so when we measure positions, or we measure velocities or accelerations or forces, or any physical quantity, almost any, it will very often depend on the frame of reference. So let's consider first the reference frame of a space shuttle. So we just mean we've got an astronaut, not drawn to scale, obviously, but sitting out here taking a spacewalk or space ride on the top of his space shuttle, and he's going to look at something out in space, whatever it is. And we've got a second reference frame where the second astronaut is just floating out in space. So he's outside the space shuttle and not attached to it. He's just kind of floating off by himself. I don't know if he got untethered from the space shuttle, in which case you feel bad for him, or if he's just sort of out and he's got a rocket pack on him, so he's fine. So anyway, we've got these two different reference frames, and now they're going to make some observations, and we're going to ask, how do those observations compare and contrast? So to make things a little more concrete, let's imagine the space shuttle is moving along at a constant velocity of 200 miles an hour. And furthermore, we're going to imagine that the astronaut on the spacecraft throws a baseball at 50 miles per hour. Now, 50 miles per hour is not a particularly impressive speed to throw a baseball at, but I imagine that it would be quite a bit more difficult while suited up like that. So we'll cut him some slack there. So he's riding on a space shuttle that's moving at 200 miles an hour. He throws a baseball at 50 miles an hour. And what we want to ask then is, what speed does this floating astronaut measure for the ball as it approaches his helmet? Okay. And so I'll pause for a second just to sort of let you take in the situation and come up with an educated guess or an expert analysis, and then we'll talk through it a little bit more. Okay, so what do you think? Well, the answer, not surprisingly, is 250 miles an hour, right? So if the space shuttle is moving at 200 miles an hour, you throw a ball at 50 miles per hour, and so the total speed of that ball approaching this helpless astronaut floating in space is 250 miles an hour. And in fact, if you're a baseball player, this is why outfielders, when they're trying to throw somebody out at home, they're going to do so on a run, right? If they can at all, they're going to be running towards where they're throwing it as they throw it, just to give the ball a little bit more oomph, right? Um, so now let's change the situation just slightly and say instead of a baseball, we're going to have this guy, the first astronaut, shine a laser. Now everybody knows you're not supposed to shine lasers at people's eyes, but apparently these astronauts are not friends. So that's what's happening. The astronaut's riding along the space shuttle, turns on a laser and points it at the astronaut. And so we're going to ask the same question. Instead of throwing a baseball now, he's throwing photons, if you will. He's throwing this laser beam at him. And so we want to ask, well, the speed of light of the laser, we know what that is, right? It's the speed of light. And even better, we're actually out in the vacuum of space, or the very near vacuum, and so it really is moving at essentially the perfect speed of light, 3 × 10⁸ meters per second. But again, he's moving at 200 miles per hour on the space shuttle. So the question that we want to ask then is, well, what speed does the stationary astronaut measure the light coming to when he receives it? And any normal thinking individual, certainly prior to about 1905, would have said, well, obviously, the speed of light is 3 × 10⁸ meters per second coming out of that laser. You get an additional 200 miles per hour from the space shuttle, and so the net result is 3 × 10⁸ plus 200 miles an hour. But it turns out we've done very careful experiments, and that is not right. In fact, the stationary astronaut measures the laser beam to be arriving at his location at exactly the speed of light, c. Okay. This is a sort of a mind-boggling result. Makes absolutely no sense in the context of what we call Newtonian mechanics, which had been, it had held the day and been universally acclaimed for over 300 years by the time that Albert Einstein came around. And it just it blew people's minds, as it continues to when you really think about it. Because what we call the classical or the Galilean addition of velocities, or Galilean relativity, that everyone, it just kind of is common sense, where you add velocities like the baseball with the space shuttle. It doesn't work when things are moving near the speed of light. And so this brings us to one of the most important tenets or principles of special relativity. This is Einstein's theory of special relativity, is that the speed of light is the same in every, what we call an inertial reference frame. And that's, just fancy terminology for saying if you have 2 reference frames which are moving at constant velocity with respect to one another, then the speed of light will be the same in both of those reference frames. It turns out that's going to have some pretty weird implications. Okay, but just to put you at ease, I'm not just spinning a tale here. We've done a lot of experiments over the last 100+ years now, and every time Einstein's relativity has been borne out. So there's a whole lot of data to support this. It makes our heads hurt every time we try to think about it, but it turns out it's true. And more to the point, we're going to need to understand something about this in order to understand those black holes that we really want to get to before the end of these lectures. So let's look at one further example where we really speed up this space shuttle to half the speed of light. Now, hard to do, but not hard to do on paper or on the PowerPoint screen. So let's imagine that. So we have a space shuttle moving at half the speed of light now, still shining a laser. Speed of light is still the same, no matter what. So again, this is going to be our starting point. As I said, there are lots of experiments that prove this is true. We're not going to do those experiments here, but if your brain hurts enough that you really want to dig into this more and aren't just running away in the other direction, you can certainly search the web. There are a lot of good resources that talk about special relativity in great detail. So just a bit of terminology. When objects travel near the speed of light, we say they're traveling at relativistic speeds. Okay, and so that's just a definition. When we say something is moving relativistically or at a relativistic speed, we mean it's near the speed of light. And the reason that it's useful to have a term like that is that I've said, sort of mind-boggling that the addition of velocities works the way that it does. Mind-boggling that the speed of light is the same in every inertial reference frame. And I further said that these are going to have some weird implications. They're going to sort of end up completely revolutionizing the way that we look at space and time. But the weird aspects of space and time that are implied by this only become relevant or noticeable when objects are traveling relativistically near the speed of light. And this makes sense because Newtonian mechanics, Galilean relativity, common sense addition of velocities, those worked really well for people for like all of human history up until 1905. Right, and so there's a reason for that. It's because it's a really, really close approximation to reality. It wasn't perfect. It turns out that Einstein's relativity superseded it, right? But it did a lot of things right. It predicted a lot of physics and astronomy correctly for a long time. And so it's only when things start traveling near the speed of light that the sort of the weirdness of nature becomes noticeable. So as I said in the last slide, Isaac Newton had developed his 3 laws of motion and laws of gravitation about 300 years before Einstein came along. And for those 300 years, they had met with just astounding success in all sorts of applications. And so there was it was the popular belief was that these laws were just Newton was a genius. He had found these laws. He understood nature. And there was other work to be done in electromagnetism and thermodynamics and other areas of physics, for example. But when it came to mechanics, Newton had put the finishing touches on perfection, as it were. But it turns out that after 300 or so years, some cracks started to appear. And among those recognizing the cracks and trying to fill them, if you will, is Albert Einstein. And so Einstein recognized that Newton's laws of motion and gravity were in fact insufficient to explain how nature worked at relativistic speeds. And so again, when things start moving near, or in the case of light, actually at the speed of light, there were the instruments of the time were finally good enough to take precise measurements and notice that there were some problems, that Newton's laws, as well as they worked at non-relativistic speeds, they started to break down, and so something else was needed. And just as a bit of trivia, Einstein published his first scientific paper at the age of 16. So he was a little bit ahead of his time. Incidentally, another bit of trivia, you may hear from time to time in the movies or on the internet or wherever that Einstein was not a good student of math. That's not true. Just so you know, he was a very good mathematician. He was not, the greatest mathematician in history. He was a physicist, not a mathematician, but he was good at math. So if you're ever trying to find an excuse to not do math or whatever, and you're tempted, or you hear somebody else say, "Well, Einstein wasn't good at math," not so. So after publishing his first paper at the age of 16, he went on to publish a number of other papers, and in particular, when he was around 25 years old, he developed and published what's now known as the theory of special relativity. And it correctly describes how objects behave when they're traveling near the speed of light. This is a picture of Einstein in 1904. He actually published the special theory of relativity in 1905. 1905, incidentally, is known as Einstein's miraculous year because he published a number of papers. I want to say the number is 6. I think that's right. 6 papers on a number of different topics, and that just were brilliantly insightful. And I don't know that anyone has ever had a year like that, where they've made such fundamental insight and progress in different areas. But there's a reason that Einstein is known as he is. And so one other caveat here, or thing that I would mention, is this theory of special relativity is very often referred to as a theory, of relativity. But when it comes to that word theory, I do want to stress that that's not a label that's hung around because there are questions about the accuracy of special relativity. So this is not a case of just a theory of special relativity. I know there are very, very few, if any, theories of physics and nature which have been tested more thoroughly than special relativity, and it has been borne out every single time. So this is very much, some things in physics get called laws, like Newton's laws, whereas here, special relativity is a theory of special relativity. But for example, special relativity is much more accurate than Newton's laws, and so the use of law and theory, it can be a little misleading sometimes in science. But just be clear, this is not just a theory; it is a very good one. So I want to talk now a little bit about a thought experiment. For any of you with German backgrounds, the term Gedunkan Experiment is very often used, which is just German for thought experiment. And this was kind of the starting place for Einstein's theory of relativity. And it starts with what we call a light clock, which is just a fancy way of saying you've got a mirror and a laser. He wouldn't have said laser because lasers were not invented in Einstein's time, not in 1905. But we'll upgrade his thought experiment to include a laser here. And so we've got a train here, and we've got this box which shines a laser out, and it's separated a distance d from a mirror on the the other side of the train. And so what we're going to do is we're going to shoot that laser up towards the mirror, and it's going to be reflected back down towards the box, right? So you turn on the laser goes up, hits the mirror, is reflected, and then comes back. So in that process, the laser beam has traveled a total distance of 2d, right? 2 times d. It went d on the way out and then d on the way back. Well, the definition of speed is just distance divided by time, right? Now we know how fast light travels. It's the speed of light, right? The name thing. And so the speed of light then is c on the left side of the equation. The distance that this light has traveled is 2d, which is here in the numerator on the right side. And then the amount of time that process took, we don't know yet. We could measure with a really good stopwatch, for example. We can measure in principle. And so we're going to call that delta t train, okay? Which, again, the labels are pretty standard labels for physics and math. The delta means a change in, quite generally. And so we're calling it delta t. That means the change in time between when the laser beam left and when it came back. And we put this subscript train on t to denote this is the time measured in the train. And more about that in a second, because we're going to make this measurement in a couple of different frames of reference, right? This delta t is the time that it took the laser to go out and come back as measured in the train. But we're also going to make that measurement from a platform, standing outside the train as this train comes by. But this is the equation for speed of light here as measured in the train. Okay. So now let's do the same experiment, but this time we're going to stand outside the train on a platform as the train moves past. Okay. And things are going to look a little different here because the train is moving, right? So the beam in particular leaves the laser box at some point in time, but the laser beam is going to appear to us not to move simply up and down, but it will also have a horizontal component of the velocity because the train is moving. So the box is moving, and so the light beam actually moves at an angle. And so we will see it leave the box, we'll see it reflect off, and we'll see it come back. Now, just to be clear, when I say we will see it, we're going to have to slow this way down to actually see the light moving. Right? Light moves very quickly. Our eyes don't actually pick up on that very well. But in principle, this can be done. And if you're interested actually in practice, now high-speed cameras are getting fast enough that this kind of thing, actually watching light move effectively, is on the verge of actually being accomplished. So that which is kind of mind-blowing itself. But anyway, from the platform, this is the path that we see the light move. But among other things, what this means is that the light beam has actually traveled a different distance in our frame of reference than it did in the train's frame of reference, right? Because this beam didn't just go straight out and straight back. Now it moved along a diagonal. And in particular, it moved along the hypotenuse of a right triangle. I hope that I didn't sort of bring back any PTSD or trigger anybody from your days of high school geometry or trigonometry, but you know, there's a reason you learned it then, and the reason is that you were being prepared for this slide right here. So so if you break down the triangle, the two legs are, one of the legs is D, which is the same distance that we talked about before, the distance between the laser box and the mirror. But then we've got the other leg, which has a length which is given by this, and that is V delta T platform divided by 2. And if that looks complicated, it's not. V delta T is just speed times time, right? V is the speed of the train. So how fast is the train moving? Delta T platform is how long is the time that it's required for the light to leave the box, go out, hit the mirror, and come back as measured on the platform. So again, you imagine you're standing on the platform watching this train come by, you pull out your watch, you see, as soon as you see the laser light leave the box, you start your watch, you see it then go out, hit the mirror, come back, and when it comes back, you stop your watch. Again, your watch would have to be better than mine to actually do this in practice, but in principle, there's no problem. And so if delta T is the amount of time it takes for the light to go out and come back, well then delta T over 2, half of that total time, is how long it takes the light just to go one way, right? And so the distance, this leg, this bottom leg of the triangle, is the distance that the train travels in the time that it takes light to go from the laser box to the mirror. Okay, so we've got D on one leg, V delta T over 2 on another leg. Incidentally, and this may or may not have bothered you, this is drawn to scale. If this is drawn to scale, then this train is moving really, really fast, right? In general, light moves really quickly, and so for any actual train speeds that are achieved on Earth, this triangle would be really, really skinny, and so much so that you would not be able to see what I'm trying to tell you. And so this is exaggerated so that you can see it. So you can either view this as not being drawn to scale, or you can imagine that this train is moving, you know, very relativistically, which is fine because, again, this is a thought experiment. So I've told you now, you observe the light traveling a longer distance, right? It's not just D out and D back. It's moving along the hypotenuse, along this longer diagonal. But you still see it moving at the speed of light, right? That's one of the tenets of special relativity. And really, I should just say it's the tenets of nature. It's how God made it. It's mind-boggling, but again, we do experiments and we verify, yeah, this really is the way that nature is made. And so now the question is, let's go back to the speed equation again. Speed equals distance over time, and see what it looks like, what that equation looks like in the platform frame of reference. And I'll give you a second to just let the beauty of this equation wash over you. No, I'm being facetious, but it looks a little bit more complicated, right? But fundamentally, it's the same thing that we did in the train's frame of reference. So on the left side of the equation, we've got the speed, right? Then on the right side of the equation, we've got distance divided by time. So the time is easy. It's just delta T platform, right? We don't know what that is yet, so we're just labeling it delta T platform. It's the time as measured by a watch on the platform that it took the light to go out, reflect, and come back. The distance, the complicated part of this equation comes in the numerator, which is the total distance traveled, and it's just twice the length of this hypotenuse, right? So if you remember back to the glorious days when you were applying the Pythagorean Theorem with regularity, that's all we're doing here. If you ever grumbled and wondered, why do I need to learn the Pythagorean Theorem? The answer was for slide 14 of this lecture, so you're welcome. And here's the expression. So you have, if you remember the Pythagorean Theorem, it's a squared plus b squared equals c squared. And so you just take the first leg, which is d, and you square it, and you add to it the length of the second leg, v delta t over 2, all squared, and then you take the square root. So the expression looks a little complicated, certainly more complicated than it looked in the train's frame of reference, but we have it now. And importantly, remember, the speed of light, the left side of this equation, c, is exactly the same in both frames, right? So now we're going to use that fact and see what does that tell us about the delta t's. Okay, so here's a little bit of math. It's sort of magical. I just said some algebra. If you want to see that algebra, I'm more than happy to go through that with you. Don't hesitate to reach out. But since the speed of light is the same in both reference frames, we can just take the two equations that we've obtained on the last couple of slides and set them equal to each other. And so remember, the right side of the equation, or the left side of this equation, which was the right side of the speed equation in the train frame, is just 2d over delta t train. And now we're setting that equal to this more complicated expression that we obtained from the platform frame of reference. And so we set those things equal, we do a little bit of algebra, and we obtain this magical expression, which is boxed for a reason. And it gives us a relationship between the time as measured in the train's frame of reference and the time as measured on the platform. And they're not the same, right? Not only are they not the same, you can see exactly how they're not the same. And in particular, because v, the speed of the train, is always less than c, we know that this term right here, v squared over c squared, will always be less than 1. And so when you take 1 minus this thing, you'll get something between 0 and 1. And when you take the square root of that, you'll get something between 0 and 1. And the upshot is that for any non-zero speed of the train, as long as the train is moving, the time as measured on the train will be less than, it will be smaller than the time measured on the platform. So if you've got one guy with a watch on the train and you've got another guy with a watch on the platform, the time measured on the train will be less than the time measured on the platform. And this is, one of the mind-boggling aspects of special relativity, or of nature, which is correctly described by special relativity. And it's a direct result. All that we used was the fact that the speed of light is the same in both of these frames of reference. Okay. Normally, normal people who didn't know this sort of oddness, that just live everyday life, would have assumed that the times were the same. That time is this uniform thing, and that we might be in different places, we might be doing completely different things, but if you measure the time between two events and I measure the time between two events, we would agree it was 7 seconds between these events, say, for example. What special relativity is saying, well, that can't be true. If the speed of light is the same in every frame of reference, then times will not be the same. Conversely, if times are the same in every frame of reference, the speed of light would not be the same in every frame of reference. But the data is in, and Einstein was right. So time dilation is the name that we give for this phenomena, where times are different as measured in different frames. And the faster something is moving, the slower time runs in that frame of reference. So that's the first major result of special relativity. And every time that I go through this, it still kind of makes my head hurt a little bit, just to let you know. I love doing the math. I love proving, deriving this fairly simply. There are a lot of derivations in physics are really cumbersome. This is not one of them. This is really elegant. But the results, you pay for in brain pain. So feel free to pause this, rewind it, watch it again. If feel free to conclude that, I have done a terrible job explaining this, that it must be much simpler if somebody else explains it, and then go Google and find somebody else talking about special relativity. It's a popular topic, so I'm sure there's a lot of good content on the web. But time dilation, one of the main results, and one that we're going to use going forward. So now that we've gotten a detailed analysis of time dilation, let's back up a little bit and look at the bigger picture. So one of the large-scale implications of Einstein's theory is that time is not an absolute quantity, that it will be measured differently by different observers who are in their own respective reference frames. The upshot of that, it turns out, is that in order to accurately describe an event, when and where something happened, we need 4 quantities, right? We need we live in 3 spatial dimensions, which we typically label X, Y, and Z, but length, width, and height. And we have 1 dimension of time. But it turns out that, as we've seen, the time is not the same in different reference frames. So in order to get a consistent definition of when and where things happen, we have to wrap these things up, have to combine space and time together. We can't treat them separately. And that combined entity is known as a 4-dimensional space-time. So again, we weren't very creative with our naming schemes. We just said, well, space and time, it turns out, they're inextricably linked in some way that we had never understood previously. They have to be, otherwise the speed of light would not be the same in every frame of reference. Now that we know it is, we've got to put these things together. And so if you've ever heard about space-time, that's what it is. It's a recognition of the fact that despite the fact that in our everyday non-relativistic lives, we can very often and almost exclusively do refer to space and time independently, fundamentally they are connected. And when things start moving relativistically, that connectivity becomes very important. And it's impossible to have a physical theory of nature that treats them separately. So they have to be combined, and that combined concept is known as a 4-dimensional space-time. And there's more. Okay, this is an equation I will not derive for you because we don't have another semester's worth of time. But the most famous equation in physics, I dare say, E equals mc squared, is a direct implication of Einstein's theory of special relativity as well. And I think I've said before, you don't get famous in physics typically for long, complicated equations. You get famous for short, beautiful equations, and it's hard to be shorter and more beautiful than this. But in addition to being a very compact mathematical expression, it's fundamentally important in what it says to us, which is that energy and mass are equivalent. Okay, and this was a completely new concept. For example, if you've taken chemistry, very often you'll invoke mass conservation. You say, well, if you have some chemical reaction, the masses before and after the reaction have to be the same. And it turns out that that's to a very, very high degree correct. It's not perfectly correct, but it is so darn close to being correct for chemical reactions that for all practical purposes you can assume it. But it turns out that for nuclear reactions, for example, it is emphatically not correct. Mass is not conserved in nuclear reactions. And in fact, the amount of mass change is very important. And we'll say a little bit more about that in a little bit. In fact, we already have seen that in the context of nuclear fusion, right? Because when we looked at bringing 4 protons together and forming an alpha particle, we looked at the mass of the 4 protons together, and we looked at the mass of the alpha particle and said they're actually a little bit different. That alpha particle is a little bit less massive than those 4 protons were. Where did the extra mass go? Well, if you recall, the answer is it was released in the form of energy, and the amount of energy is given exactly by this equation of Einstein. And so if you imagine trying to construct an object from scratch, so you have nothing and now you want to build something up, whether it's a molecule or even just an atom or a baseball. It would take energy to create all the protons and neutrons and all the electrons and put them together. How much energy is given by E equals mc squared. But not only does it take energy to create the mass, it takes energy to move that mass, or to more properly, to accelerate the mass. And it turns out the closer an object gets to the speed of light, the more additional energy it takes. So in order to take a baseball and throw it, move it from rest to 1 mile an hour, that doesn't take very much energy. To move it from, at half the speed of light takes a lot more energy. But the closer you get to the speed of light, the more additional energy it takes. And the result is that it would, in fact, take an infinite amount of energy to accelerate even a single electron to the full speed of light. So we can get really, really close. So as I've written here, 99.999999, however many 9% of the speed of light, we can get there. But we'll never, it's impossible to get to the speed of light itself. And so the speed of light is sometimes referred to as a universal speed barrier. There are lots of people out there on the internet and in sci-fi and things like that that talk about moving faster than the speed of light, warp drives and things like that. And that's something that we could talk about in some detail as well. But we are very confident that it is impossible to travel faster than the speed of light. There are some caveats. If you insist on caveats about wormholes, for example, that's something we could talk about. We're not going to talk about now. So there is a wormhole may provide a way to, in principle, effectively travel faster than the speed of light, but not really. And so again, I don't want to go into details there, just to say nothing can travel faster than the speed of light. And one way of understanding that is that it would take an infinite amount of energy in order to accelerate something to that speed. So now that we know that objects with mass can never travel the speed of light, and that's important. It's the mass. If something doesn't have mass, like a photon, a particle of light, has no mass. That will travel at the speed of light. But objects with mass cannot travel at the speed of light. And so if you look, for example, here at this plot, at which represents a rocket ship accelerating at gravitational acceleration. So you imagine you get out into outer space, you're in a rocket ship, and you say, okay, I'm going to turn on the rockets, and I'm going to accelerate at 9.8 meters per second squared, which is gravitational acceleration on the surface of Earth. According to Newton's theory, Newton's laws of physics, that acceleration would result in a linear increase in the velocity as a function of time. It would just continue speeding up. And then around very close to a year after you started accelerating, you would pass the speed of light. In contrast, if you try to do that with according to to Einstein's theory of relativity, you can see the result is very different. And so initially, Newton's law and special relativity agree very well, but the faster the rocket ship gets, the closer to the speed of light it gets, the harder it is to increase further. And so this curve ends up bending over and only asymptotically approaching the speed of light. And so you'll see that, it gets closer and closer to the speed of light, but it gets harder and harder to do it. And so it will never actually make it. So big differences. And again, these have been tested a myriad of times, and Einstein, it turns out, is always right. So why do we talk about this? Or what difference can it make? And how do we actually know this is true? Well, one of the coolest tests of special relativity comes in the form of muon observations from the Earth's upper atmosphere. So, and the reason is that I've said that the relativistic effects of time dilation, for example, they're only relevant when objects are moving relativistically, right? And so something has to be moving near the speed of light before you start to actually see practical effects of time dilation. So the natural thought is, well, if we want to test this, then we need to look around for something that's moving near the speed of light. Well, massive things that have significant mass, like the mass of a baseball again, or whatever, it's really hard to get those things moving the speed of light, near the speed of light. So the idea then is, well, let's look for something really light, something with really low mass, so that it's easier to speed that up. And a great example is a muon. So a muon is a subatomic particle that you can think of as a heavy electron. It's about 200 times as massive as an electron, but otherwise has very similar properties. It has a negative charge, and has various other quantum mechanical properties that are very similar to the electron. And these are relevant because they're created in our upper atmosphere when cosmic rays strike the atmosphere. And because they're so light, they travel near the speed of light as they move through the atmosphere. And so it turns out that we can detect these things. And so they give us a kind of a great, we didn't even have to create to build an apparatus or to build a lab to create these muons. Nature is creating them all the time. And so the question is, well, what can we do with these things? How can we use them to test special relativity? So let's imagine that 1,000 muons are produced at a height of 15 kilometers, just to pick a number. Well, the number of muons that reach the ground before they decay varies with the speed of the muon. And so let me pause first and tell you that the reason this decaying is happening is that muons are unstable particles. They radioactively decay. And how long they take to decay, in the laboratory, if I just create a muon at rest, there's a well-defined, what we call a half-life. So you never know when a particular muon will decay, but you know if you have a whole bunch of muons, after one half-life, you'll have half of them will be left. And then you go another half-life and another half will have decayed and so on. So we understand muon decay quite well. But it turns out that if you think about this from the muon's perspective, the muon is effectively sitting there in the lab, again, and you can imagine it looking at its watch and deciding when to decay. And so it knows what its half-life is, it knows about how long it should live, and it's going to, once it reaches that time, it will decay. But we've talked about time dilation now, and so we understand that the time as measured in the muon's frame of reference is different than the time as measured on the ground, because these muons are moving. And how different those times are varies with how fast these muons are moving. Okay? And so the upshot is that if a muon happened to be moving at 90% the speed of light, or 0.9 c, then out of 1,000 muons, about 1 would reach the surface of the Earth before it decayed. Okay, so almost all of them would be gone. On the other hand, if it was moving at 99% the speed of light, then we would get over 10% of the muons. They would still be alive. Say 108 muons would not yet have decayed by the time they hit the Earth. If you increase it to 99.9% the speed of light, 495 of these muons reach the ground. And finally, if we go to 99.99% of the speed of light, the rate at which time flows in the muon's frame of reference has fallen by such a degree that a full 80% of those muons reach the ground. Okay, so it's a really cool test because you effectively have clocks on these muons by virtue of the fact that they radioactively decay. Right? We can't put an actual clock on a muon, but they effectively have an internal clock by virtue of their instability to radioactive decay. And so by using that decay, we can look at, well, how many of these things are being produced in the upper atmosphere? How many do we observe on Earth? And then we can compare, well, what does that tell us about time dilation? And it turns out, as you might have guessed, it tells us Einstein was right. But there's another way to look at this too. And so we've talked about time dilation, which says that time runs slower when you're moving fast. Okay, but there's something else that happens too, which is called length contraction. And that means that lengths appear shorter when you're moving very fast. So if it didn't bother you enough that time is not constant between different frames of reference, well, it turns out lengths are also not constant. Wouldn't it have been much easier if the speed of light were not constant in every frame of reference? But that's the way it was made, and so here we are to try to understand it. So from our perspective here on Earth, as we've said, it looks like the muon's internal clock is running slow, and that's why they reach the ground, because their clock is running slower due to time dilation, and so they wait until their clock, till their alarm goes off to decay, so to speak. And so they haven't decayed by the time they hit the ground because their clock is running slowly. That's from our perspective. But what about from the muon's perspective? Because if you look at the muon's frame of reference, the muon is just standing still while the Earth is coming up at it, right? So, and I should point out again, everything is at rest in its own frame of reference, right? I'm at rest in my frame of reference, you're at rest in your frame of reference, and so on. So from the muon's point of view, it's just minding its own business while the Earth comes up to meet it. So why on earth hasn't it decayed in the muon's frame of reference? Because in its own frame of reference, again, and I know that there's a lot of opportunity for confusion here, but from the muon standpoint, it's just looking at its clock. It doesn't think it's running slow. It's looking at it, and it looks like it's running just fine. So why didn't the muon decay? Well, from the muon's perspective, it looks like the distance from the upper atmosphere to the ground is much shorter than 15 kilometers. Because it looks at the Earth and says, oh, the Earth is coming up towards me at 99% the speed of light. And because of that, that 15 kilometers is shortened. And it turns out that the amount by which that lengths are contracted is exactly the same factor by which times are dilated. And so the mind bending continues, but the almost miraculous result is that the result of whether the muon hits the Earth before decaying or not is exactly the same as measured in the muon's frame of reference as it is in our frame of reference here on the Earth. But the reasons that those two frames of reference would give for it are different. We would ascribe the result to time dilation. The muon would ascribe the result to length contraction, but the results are exactly the same. And that's one of the most important aspects of special relativity, or any valid theory of physics for that matter, is that the predictions of the theory need to be independent of the frame of reference in which you do the calculation. For things like, did the muon strike the Earth before it decayed? Right? That's not a question that should depend upon a frame of reference. So now that I've completely confused you and obliterated any sense of understanding of the world that we live in, let's look at an example or a question, another thought experiment. So let's suppose that you're sitting on Earth and you have a friend who's flying past in a spaceship, and both of you measured the time that it takes for the spaceship to pass by Earth. Which of the following is true? So answer A is the time you measure is longer than the time your friend measures. B is the time that you measure is shorter than the time your friend measures. And C is you both measure the same amount of time. So I'll pause for my customary 30 seconds or so, let it sink in. As always, you're welcome to pause this and ponder it to your heart's content, and then we'll come back and I'll ruin the surprise. Okay, well, let's see what happened here. Well, the correct answer is A. So the time that you measure on Earth is longer than the time your friend measures. And this is just a classic example of time dilation, right? Time slows down, clocks slow down when you're moving faster. And so you're sitting here on Earth while the spacecraft flies by. The spacecraft is moving faster, and so the time as measured on the spacecraft by your friend will be less than the time as measured by you on Earth. So now let's look at a different question. Now which of the following is true? The distance between the Earth and the space shuttle is farther, according to you on Earth, or the distance between the Earth and the space shuttle is farther, according to your friend on the space shuttle, or you both measure the same distance. And again, I'll pause and let you consider. Okay, so I'm going to tell you the answer, but pause it if you don't want it yet. Okay, so the distance between the Earth and the space shuttle is farther according to you. And as you may have guessed, or if not guessed, understood very deeply, this is a classic example of length contraction. So your friend is moving at some speed. I don't know if it's still the 200 miles per hour that space shuttle was moving earlier, but he's moving at some speed. And because he's moving, lengths contract. And so the distance between him and the Earth is shorter as measured in his reference frame than it is as measured in your reference frame. So now this brings us to one of the classic questions, paradoxes in special relativity. And so you'll find books, myriad books out there that will spend an inordinate amount of time talking about the twin paradox. And so we're going to imagine the following situation. You have a twin, and you're going to stay here on Earth while your twin blasts off in a space shuttle and moves near the speed of light away from the Earth for some period of time, say 10 years if you want to be concrete. And then after 10 years, your twin is going to slow down, he's going to turn around and come back, spend 10 more years traveling back home. And the question is, well, which one of you is older after you return? So let me pause, and you can think. Okay, well, if you want to think more, pause me before I ruin the surprise. Well, I haven't ruined it yet. Who's going to be older, the twin on Earth, the twin in the space shuttle, or are they the same age? Well, turns out the twin on Earth is older, and again, this is a case of time dilation. Now, there are. I'm going to tell you that one way of understanding this is that the twin moving away moved at some speed. He spent 10 years moving very quickly, then he turned around, then he moved back very quickly 10 more years, and all that time while he's moving so quickly, his clock is running slowly. And so I want to, as a result, here on Earth 20 years have passed, but on his clock maybe only a year has passed. And so now you started off with two twins, and now one of the twins is 19 years older than the other because their clocks ran at different rates. And one point that I want to impress upon you is the fact that this is not, it's a thought experiment because we have not actually sent a twin out for 20 years on a space shuttle. But this really would happen. So it's not, when I say that clocks run more slowly, for example, I don't mean that there's some like funny business inside the clock that the mechanisms don't work quite right, they get messed up, but that everything's really just the same. When a clock runs slowly here, I mean, every time really did slow down, relatively speaking. And so, the biological clock, for example, of this, all of the biological functions and so on, proceed in exactly the same way as that according to the slower clock. And so if you could do this experiment, the twin that came back really would be younger. And in fact, we have done this experiment, not with astronauts, but with atomic clocks that can be measured, that are used to measure time extremely precisely. We've we've synchronized two atomic clocks, put one of those clocks on a high-speed jet, flew it around the world, a time or two, I actually don't know how many times when they've done this experiment, but then they bring those two back together and they compare the clocks, and they are different, and the difference, the amount by which they're different, exactly matches the predictions of special relativity. So all of this is mind-bending stuff, but again, I don't know of any theory in the history of science that has been tested as thoroughly as special relativity, and every single time, without exception, it has been proven correctly. If you remember, about 10 years ago or so, 10 to 15, there was a case of reported superluminal neutrinos, which just means neutrinos that looked like they were traveling faster than the speed of light somewhere in Europe. And this caused great consternation and excitement because this would violate special relativity, for example, and so there was much excitement and interest, and then eventually they discovered that no, there had been an error in the analysis, and that no, they traveled less than the speed of light. So without exception, special relativity has passed with flying colors, and everybody anticipates it will continue to do so. So anyway, I told you that this would be mind-bending and mind-boggling, and I expect that it has been. Again, every time I go through this, it kind of makes my brain bend over in sometimes uncomfortable ways as well. So you are not alone. The good news is the more time you spend with it, the less painful it gets. Whether that's because we actually understand it better or whether we just get beaten into submission, sometimes I don't know. but we do the best we can. So thanks for sticking with me. I appreciate your attention on this, I think, interesting but in many ways challenging subject matter. We will move on from this in the next lecture and begin discussing Einstein's general theory of relativity, which generalizes, as the name suggests, the theory of special relativity, and very importantly, gives us a new framework for understanding gravity, which is where we finally are able to tie back in with things that actually look like astronomy, and in particular start discussing black holes in some detail. So thanks again for your attention, and I'll look forward to seeing you next time.